Hi folks, welcome back to 3.7, the video about rational functions in general. And so in this video, we're going to take a look at one example, okay? And as you can see by this page, we've got a lot of information that we're trying to answer here, right? So in this case, the only thing we're given is the equation or the function. And it turns out from here that we can actually find out everything there is to know in terms of intercepts and discontinuities and end behavior and domain. All of that is there, okay? So to begin, the very first thing we're going to do is make sure that everything is factored. Factor if needed. And in this case, our numerator needs to be factored, but our denominator is just fine, okay? And so let's go ahead and copy down the denominator. And then we're going to go ahead and factor the numerator up in this space, all right? So here we go. And we're going to go ahead and do the x. Let's see, we want to do a times c on the top, so -6. And on the bottom, we have b, which is -1. And so we want to write two numbers that multiply to make -6, but add to make -1. And so I think about that. I know 3 and 2 make 6 if I multiply, but I got to add them to make -1. So if I make the 3 negative, -3 plus 2 gives me -1. All right. What does that mean? That means that we can write x squared minus x minus 6 as x squared minus 3x plus 2x minus 6. Right? So again, we're taking that middle term and we're splitting it into two unsimplified terms that actually combine to give us what we started. And the reason we're doing that is so that we can group the first two terms and group the second two terms so that we can factor. All right, greatest common factor for the first two is just x, so x minus 3, plus greatest common factor for the second two is 2. And so we're left with x minus 3. Now remember, x minus 3 and x minus 3, those should match, right? When they match, we know we factored correctly. Now we've got one last step, and that is to bring the x minus 3 to the front. What are we left with? X plus 2. All right, so x minus 3 times x plus 2 is what I'm going to write for my numerator. X minus 3, x plus 2. Okay. All right, so we're going to factor. Now, after we factored, we really have our choice in terms of where we want to start, okay? So I know that when we were doing graphing the parabolas, we sort of labeled where we wanted to start. I think what would be good here is to start with our discontinuities, all right? And then talk about our end behavior, just because those are the three new pieces of information, right? So we want to make sure while our brains are a little bit more fresh that we really understand the stuff we just learned. Then we're going to go back. We're going to find our y-intercept. We're going to find our x-intercept. And after we found all of those, then we're going to go ahead and fill in our domain. And last but not least, we're going to put most of the important features on the graph, all right? But as you can see here, it says use Desmos to graph the function. Make sure that you label any important characteristics. So really, I don't need us to graph all of this by hand, but I think it's useful to mark the characteristics, and then we'll check with Desmos and see how well it matches, okay? So with these kinds of problems, we can actually tell whether we're right or not based off of what the picture looks like, okay? All right, my friends, let's begin. Discontinuities from a number over 0, right? So this means I'm looking for terms in the denominator that are not in the numerator, okay? And so if I zoom in over here, I might see that I've got this factor. If I plug in 2, I'm going to get 0 on the bottom. And this one, oops, if I plug in -1 on the bottom, I'm also going to get 0, okay? And those two factors are not on the top. So that means that for my discontinuities from a number equal over 0, right? This is our vertical asymptotes. We take our 2, so x minus 2 equals 0, and x plus 1 equals 0. We solve for x. And those are the equations for our two vertical asymptotes. X equals 2 and x equals -1, all right? So it's okay for us to have more than one vertical asymptote. And in fact, I'm going to go ahead and sketch those right on our graph. So at, I believe we said -1 and 2. Okay, and while we're here, let's go ahead and write the equations. X equals 2 and x equals -1. All right, so we've got our vertical asymptotes, and I bet if when we go to Desmos, we'll be able to see those pretty clearly. Okay. All right. Next, we're going to look for what happens when we have a number that makes the top and the bottom 0. And that, as a reminder, looks like a hole on our function. But if we look back at our equation, there's no factors that are on the bottom and on the top, right? They're all different. Now, for example, if this had been a 2 instead of a 3, then this would have been a hole, not a vertical asymptote, okay? So in this case, I actually don't have any holes, all right? So we should write here, no holes, because there are no common factors between the numerator and the denominator, okay? Between the numerator and denominator, all right? Now, I wanted to make sure we wrote this explanation because maybe it makes sense right now, but when we're coming back to study, I want us to know, okay, this is why we don't have a hole here, okay? All right, so discontinuities we just learned about, and now let's go back to that end behavior piece, okay? So it says determine whether the rational function has a horizontal asymptote of y equals 0, y equals a number, or a slant asymptote. Then explain your reasoning, okay? So sometimes it's hard for us to write explanations. That's why I want to take the time to model this right now, because whatever we write here, you can always change the words a little bit or change the numbers to match whatever problem you're working on, okay? Now, let's go back, and when we look at our function, the thing that we're focusing on now is not the factors themselves, but more how many factors, because that actually tells us about the degree, okay? So let's go back to the top. I notice that this numerator has 2 factors, right? So it's in factored form. In factored form, I add my powers. So 1 plus 1 means that the numerator has degree 2. What's the degree of the bottom? Well, I have 1 and 2. So this is degree 3. All right, degree 2 and degree 3. Degree 2 is smaller than degree 3. What does that mean then? If we have a degree that is smaller on the top, that's when we have the horizontal asymptote of y equals 0. Okay, so let's take the time to write that out. Notice that the numerator is degree 2, and the denominator is degree 3. All right, so notice that the numerator is degree 2 and the denominator is degree 3. Since 2 is less than 3, okay, f of x has a horizontal asymptote at y equals 0. Okay, so I know that that's a lot of words, but 2 reasons why I want us to take the time to write it. One, I think it's important that we're able to explain ourselves mathematically. I mean, in regular life, but also mathematically. And 2, the more that we write something, the stickier it is for our brains, right? So when we're in a high stress situation, like an exam, or maybe when you need this information, which you do in Calc 1, we want to have it readily available to us. And so the more we write it, the stickier it is for our brains, okay? All right, so we've taken care of all the new stuff we learned. Now let's go back and review some of the old stuff, our x-intercepts, our y-intercepts, okay? Because even though the function is different, the process is still the same. So y-intercept means 0, comma, a number. X-intercept means number, comma, 0. That does not change. So let's do our y-intercept first. I take my function, everywhere I see an x, I'm going to plug in 0, okay? And it doesn't matter whether you plug it into the original or the factored. It's really up to you. I'm going to go ahead and plug it into the factored form, just because I personally like to work in factored form when I can, but it doesn't matter if you do the other one. So 0 minus 3, 0 plus 2 over 0 minus 2 times 0 plus 1 squared. All right, let's be really careful here. I've got negative 3 times positive 2, that's negative 6. And I've got negative 2 times 1, which is negative 2. And that means that I end up not with a negative 3, but with a positive 3, okay? So my y-intercept, but let's make sure we write this as a coordinate. So I'm going to shrink this a little bit, and our coordinate is 0, comma, 3. Let's go ahead and put that on our graph. All right, so 0, comma, 3 would be somewhere up here, okay? All right, let's do our x-intercepts now. So here's a big concept for us, okay? And I think on some level we know it, but when we're in the middle of all these numbers and letters, sometimes we forget, okay? So let's come up here a little bit. And in this space right here, I'm going to ask us a few questions, right? What is 0 divided by 1? And I hope we all say 0, okay? What about 0 divided by 4? And I hope we all say 0. What about 0 divided by negative 11? And I hope we say 0. And maybe we see where I'm going with this, which is that anytime you have 0 divided by a number, we end up with 0, okay? This is a super important concept in mathematics, because when we take a 0 and we divide it by any number that's not 0, we end up with 0. So even though we want to do this, we want to take x squared minus x minus 6 over x minus 2 times x plus 1 squared equal to 0. We have a fraction and we want to equal 0. The only thing we really need to do is find out when the numerator equals 0, okay? In other words, x minus 3 times x plus 2 equals 0, okay? We don't need to worry about that denominator because the only way we get 0 out of a fraction is when the top is equal to 0, right? Now, this gives us x equals 3. This gives us x equals -2. So we have two x-intercepts, 3, 0 and -2, 0. Now, these two intercepts would be, let's see, 3, 0 and -2, 0. Okay. All right. So far we've done 1, 2, 3, 4, 5. I believe this was supposed to be 6 and 7, not 7 and 8. Don't tell anyone your math teacher can't count. 6 and 7. Okay. So the domain, all right, it says express the domain in interval notation, then explain your reasoning. Okay, so let's think about what x values we can't have. We can have all the x values over here, or we can have all the ones here, and all the ones over here. But what we cannot have is -1 and 2. Because when we put -1 or 2 into our equation, we end up dividing by 0, and that's not okay. All right. So our domain here is going to be this. Domain is from -infinity to -1 in union with -1 to 2 in union with 2 to infinity. Okay. And our reasoning is something like this. Because we have vertical asymptotes at x equals -1 and 2, those values cannot be in the domain, right? Those values cannot be in the domain. And that, my friends, would be sufficient to explain what you've written here. Okay, so let's get this problem all on one page for you. Ooh, almost, there we go. All right, and we're going to come back here for the video part 3, in which we'll go over one more example. All right, I'll see you folks back here.